Good morning, good afternoon, good evening, good night, everyone. Welcome back to the Womanium Global Quantum and AI Program 2024. Meanwhile, week 3, day 10. Today, we will focus on AI. We have two sessions. The first session will be done by a colleague of Brian McDermott at the Naval Nuclear Lab, Jon Ruffley, talking about AI for materials design. And the second talk will be by Sam Stanwyck from NVIDIA about AI, quantum, and HPCs, topics I'm sure you will all be very interested in. Lindsay, could you please introduce our first speaker, Dr. Jon Ruffley?
Absolutely. We're so grateful to have him here today with the program. Jon Ruffley is a senior engineer in the Naval Nuclear Lab's Advanced Technology Innovation Subdivision. NNL develops advanced naval nuclear propulsion technology for the United States Navy. And Jon is interested in difficult engineering problems, regardless of the form they take. He's currently working on the design of additively manufacturable metals with artificial intelligence. He works with universities, national labs, and industry to develop additional technologies with applications to the Naval Nuclear Propulsion Program. Before coming to NNL, he worked for Calgon Carbon in process engineering, research and development, and he is excited to join the lab for the opportunity to help develop technology for the world's best Navy. Jon received his Bachelor of Science in Chemical Engineering from the Ohio State University and his PhD in Chemical Engineering from the University of Pittsburgh under Carl Johnson. He also had the opportunity to spend a summer on fellowship at the Army Research Laboratory, and he's the president of the Ohio State University Alumni Club of Pittsburgh. He also enjoys Brazilian Jiu-Jitsu and reading military and geopolitical history. He is the vice chair of the Industry Advisory Board of MDS Rely, a National Science Foundation Industry University Cooperative Research Center. Thank you so much for joining us, and we're looking forward to hearing from you today.
Thanks everyone for joining us today. I'm very excited about this. I always like taking the opportunity to talk to people about technology, technological development, and basically the whole kitchen sink of things that are possible. So, we're going to talk a little bit about AI for materials design, and this is going to be somewhat of a non technical talk from a details level. We'll do a high level overview of a variety of topics. Disclaimer: these opinions are not those of my employer, the typical day of this day and age. So nothing I say is the Naval Nuclear Lab's opinion, but I'm very thankful for they gave me the opportunity to come talk to you all. So, as was mentioned, I have a bachelor's and a PhD in chemical engineering, and I worked for Calgon Carbon before coming to the Naval Nuclear Lab. One of like to put an image in your heads about the types of engineering problems we solve, they're extremely difficult. And as an example, when we field new warships, we send engineers out for shock trials, which is basically we detonate ordnance nearby to the vessels and make sure that all the engineering systems still work. So there are a whole bunch of really difficult engineering problems involved in that, and really problems you don't find almost anywhere else in any other field. And that's kind of what drew me to the lab, and I love my job. I have one of the coolest jobs. So we're going to start off by talking about the art of the impossible to kind of set the stage for the things that we try to achieve in a technological standpoint. In 1903, the New York Times published an article where the gist of it was basically we are wasting our time trying to fly. It will take from 1 to 10 million years for of continuous effort by mathematicians and mechanicians, which we would now call machinists and mechanical engineers, to figure out how to make flying aircraft. And I'm going to read a little bit of it directly. Provided, of course, we can meanwhile eliminate such little drawbacks and embarrassments as the existing relation between weight and strength in inorganic materials. So you can see it's a pretty snarky little piece. And 9 weeks later, the Wright brothers flew at Kitty Hawk, same year. So that should, I hope, set the stage for all the things that we attempt to accomplish in technology. Is that there will continually be people that tell us you can't do it, and you won't do it, or the things you're thinking of are ridiculous or crazy, or they'll roll their eyes at your idea, but don't ever let that stop you. Um, because about 60 years later, the Soviets put Yuri Gagarin on the into orbit. An exceptionally brave brave man to say, yeah, go ahead. You can strap me into a rocket and launch me into space, and it'll probably be okay. And 8 years after that, well, based on that, the United States launched the Apollo program, and 8 years after that, the United States had landed astronauts on the moon. And the paper of record, 66 years after saying, "Oh, flight is impossible; it'll take millions, tens of millions of years," is writing, entire full-page articles about everything that we discovered from the moon trip. So I always try to keep things like this in mind because they really frame that problem of, oh, we can't do this, we can't do that, we don't know how, it's too hard, it's too expensive, 100,000 reasons why you can't. But the reality is, most of the time we actually can. For those of us on the younger side, myself included, those things happened a long time ago. My dad will tell me stories about watching the moon landing on his parents' black and white TV set, but there are some things that we've done since then that are really great technological feats. So if we start at the top left here, we have the F-117A. It's a stealth fighter developed by Lockheed Martin's Skunk Works. Um, what makes it so stealthy is that it has a small radar cross section. And so I'm going to talk about a variety of engineering disciplines and technologies, and I'll do my best to make those as accessible to everyone, regardless of your background, as I can. So basically, what happens is, when you have angled planes in this aircraft, the radar does not bounce back in the same direction it came. So uh, a seeking dish will send out a signal, and it will get nothing back and say, oh, there's nothing there, or we only detect really small things, so those are probably like birds and artifacts. This is a fairly large aircraft. Its radar cross section is the size of a baseball, so it basically looked kind of like the size of a crow or another medium-sized bird on radar. The United States used these to great effect in the Gulf War. They were basically completely undetectable by ground radar systems. The engineering that went into this were there are a variety of ways. The first one was figuring out how to make a shape that would minimize this radar cross section so that the plane would effectively be undetectable. And then once the design was completed by the drafters, figuring out how to keep that thing in the air. It's like trying to make a rock fly. It is not easy at all. The computer systems that were developed to support this um, really started to push some of our computational technologies to keep that aircraft flying, because it is unstable. If the computers turn off, it falls out of the sky. The second example is another Lockheed product, the SR-71, also called the Blackbird, depending on which variant of the aircraft we're talking about. There are a ton of technological challenges that went into this, from the fuel systems to the engines to um, the temperature controls to keep the pilot at a reasonable temperature while going Mach 3. This is a very fast aircraft for anyone that's not familiar. It was one of the first supersonic craft that's manned. Uh, and the biggest difficulty with it was what metals to make out of, because of the temperature gradients from the leading edge to the trailing edge of the aircraft when it was traveling around at thousands of miles an hour. And the engineering solution to that was, well, we're going to make this out of titanium. The problem was titanium was and still is extremely difficult to work with. So not only do you have, again, the design problem, but it's how do you actually bring that design to reality? There are multiple engineering problems, layers of engineering problems that these guys were figuring out without any of the modern computational simulation tools, the analytical tools that we have today. Um, Example three, this is the USS Nautilus. It is the world's first nuclear powered submarine. And the Nautilus was launched in 1954. And that is 12 years after the world's first critical nuclear reactor, which was Chicago Pile 1, which was exactly a pile. I think about it like if you're familiar with the game Jenga, where there were basically blocks of graphite and uranium put into this, and you'd start removing some of the graphite, which is a moderator. So basically, it prevents the reactor from going critical. You start removing that, it went critical. 12 years later, a warship was powered by those. Again, none of the modern analytical or computational tools we have today to achieve that. That's something that we, as the Naval Nuclear Lab, are very proud of our accomplishment there. An extremely modern one is the Apple iPhone. In the early 2000s, Apple was selling a ton of iPods, and there were everybody was making, all the tech companies were making flip phones, and Apple wanted to get um, their iTunes software onto these flip phones. They were working with Motorola, if I recall correctly, and the products were kind of junky, and Steve Jobs hated it and considered it a huge embarrassment for the company. So two main designs were created at Apple to create their own phone. One was like, think of an iPod, a very simple, the older iPods, if you're old enough to remember those, that had little track wheels on them that you could go back and forth and search your music. And there was this little switch on their prototype, and you'd switch it from that into phone mode, and the color of the screen would change from, I believe, from blue to gold. And you could then use that little wheel to press different parts of it to get different numbers. And it was a phone, and not in the modern sense of phones. It played music, and like you could call your parents on it. And that was about it. The competing vision was, well, let's take Mac OS and shove that into a tiny computer in your pocket. And the amount of engineering challenges and difficulties that went on during that program caused a large number of the engineers to get divorced. And there are a lot of stories about that, how their spouses would be pretty angry at them and be like, I haven't seen you in weeks. You're working all the time. Like, we're calling it quits. Because to make the capacitive touchscreens work, to figure out how to integrate the apps, what apps to put on it, how to fit everything inside the little box, make it look nice, make it reliable, was really, really difficult. But over and over again, when humanity is faced with motivations, with challenges of things that we want to do, we are successful. So the purpose of this talk is to talk about AI and materials. So what is AI? And you'll get dictionary definitions and all those sort of things. But I like to think about AI in fairly simple terms. Um, AI is something that we've basically been doing for a long time. It's using mathematical models to make generalizable models of data, and then using those models to make future predictions about things that you might make or how something would work, or to find information that's stored within the model, or to generate text, whatever it happens to be. And we've started to also integrate the action on those predictions. Um, with time, more of this process has become computerized and automated, and our best models are no longer represented by simple functions, and modern robotics can do way more than it has been able to in the past. And a lot of this happened fairly quickly. When I was an undergrad from 2011 to 2015, if you were working in the field of AI, you were most likely a computer science PhD or a mathematics PhD, writing optimizer functions, um, working on some of the first neural networks we actually had computing power that could run neural networks. By the time I was in grad school, TensorFlow was released, where you could basically just go plug and play a whole bunch of this stuff. You didn't have to know the underlying mathematics. You had to have a general idea of how it worked, but you could go make your own image recognition algorithm. And in the current day, you can download some. Uh, I just saw a demonstration last week of a piece of software where you can give it a data file and say, hey, can make me a Python script for this, and I want you to graph this data, and I want you to graph it like this, and it will write the code for you and make the graph, to the point where you don't even have to know how to write software. And all that's happened in about the past 15 years. So the second part of the title of this talk is materials design. So what's materials design mean? And this is a place where I get into a lot of intellectual debates, because my definition is really broad. The things that people agree on is like, oh, materials design is new alloys or soft materials or ceramics, or designing the ones that already exist. But I take a much more broad approach, where it's not just making new materials, but it might be making a new geometry of material. So this is a gyroidal triply periodic minimal surface, that you can't really make those without additive manufacturing. So we're now adding in another new technology into materials design. And computers can design these structures and how to optimize them, how thick they should be, um, make suggestions for what material you would like based on how easy it is to crush this, or how strong you'd like it to be, whether you want to have it as a heat exchanger application, etc. And then there's the problem of new classes of materials. I think a lot about I guess, technologies that we've had in antiquity, like Roman roads and the aqueducts and things like that. And Romans didn't use electricity to pump their water around, and they didn't use steel or plastic pipes because they didn't have those available. In fact, a lot of the downfall of Rome has been attributed to putting lead into pipes, and that's caused lead poisoning. And some people say that the lead poisoning has led Romans to become less intelligent, and their society collapsed. Whether you believe such things or not is immaterial, but they were using these big, huge stoneworks and brickworks to carry their water around. And if you have an older house, at least in the United States, a lot of your piping systems are just going to be entirely metal. You'll have copper that's welded or that's soldered together with lead, and you might have cast iron drain pipes. If you live in a modern house, your pipes are probably all made out of polyvinyl chloride. So the first plastics were patented slightly over 100 years ago. It was an unknown material. So I try to get out into these spaces far ahead of technology and say, what's possible? What might exist that we don't know about yet? And if I figured it out, what could I do with it? So, what's our motivation for materials? A lot of times I'll have discussions with engineers and they'll say, well, this technology is really cool. And that's their motivation. Like, we should study this because it's really cool. I'm an applications person. I'm always thinking about, I want to do X, therefore I need material Y and I need it to work like Z. So we use materials to make tools, and we use tools to make materials. We use tools to complete tasks, we use them to make machines, and as our society has become more technologically advanced over the past couple hundred years, our demand for machines and tools has increased massively. Um, your older sorts of tools like crowbars, hammers, screwdrivers and things like that, all the way to some complicated nano indenting tools, the Hisotron 990, which can do like 5,000 indentations in like a square inch or something like that, some crazy numbers, and get all these material properties out of it. And this is a really circular problem. The common limitation on making new materials, like I talked about with the Blackbird example, is making the tooling to make those materials. And to make those tools, you need the materials that those tools are made out of. A good example of this, I think, is stamping automobile doors. So the door is made out of steel, and that's usually plate steel, so it's rolled. You need a machine to make that. You need furnaces. You need mining equipment to get the ores out of the ground. You also need to make the dies to press the door panels in place. And to make those dies, you need tools. And to make those tools, you need additional tools. And to make those tools, you need additional tools all the way down. So all the tools and all the materials we have, I think about them, they're kind of like this giant pyramid where everything we do is built on, really all the way back to the Bronze Age, thousands and thousands of years of figuring out how to solve problems by making tools. And for those, we need materials. So our technology compounds, and we'll have things in 30 years that we probably can't even imagine today. Maybe some science fiction writer has an idea and they're writing a novel about it right now. Um, an interesting counterpoint to that is we have recent technology that few people still know how to use, and data storage media that are close to extinction. My wife and I are expecting our third child, and we had some strong storms in the city we live in earlier this week, and we had one of her maternity appointments. We got to the doctor's office and they didn't have internet. They said, "Well, we've had our records in the computers for the past 20 years." And the nurse told us, it's been 20 years since I had to write a paper medical record, and I don't really remember how to do it because I'm so used to entering everything into the software. Uh, Growing up, we had cassette tapes to play music on. If you're a younger person, you might not even have ever physically held a cassette tape. I haven't touched one in years. We quickly moved to CDs, then to iPods, and now everything is just streamed. If you use Microsoft Word, you'll sometimes take an older file format and it'll say, hey, do you want to convert this to the newer file format? Just a warning, some features may not be compatible anymore. And eventually you get to the point where you have data storage materials like 8-track tapes or microfiche that you can find some readers for those on eBay, but they're not that easy to come by anymore. So how do we continue to develop our technology without completely losing the ability to do things that we've done before? Is an interesting question to think about. So that begs the question, what do we do with AI materials? There's a recent paper, I believe it came from a university in South Korea, where they proposed this new superconductor, and there's been a bunch of controversy of people trying to repeat that work and have had difficulty doing so. Refractory high entropy alloys for super high temperature applications. There's a lot of talk about supersonic flight, space flight, things like that. You're going to need new alloys to do those kinds of things to survive those types of harsh environments. Pharmaceuticals, I'll talk a little bit more about pharmaceutical developments towards the end of the talk, but the new drugs that have been developed, the mRNA vaccinations for COVID, are really technological marvels, and those are things that we're continuing to push forward. And AI is helping us to do a lot of those things today. And so I always will ask this question over and over and over again: what might we imagine based on those technologies? What ideas will you all come up with in the future and in your careers? A counterpoint is we need to be careful when we create new technology, because we usually have an idea of something positive that we want to do with a piece of technology. It might be a medical implant, it might be something that improves people's health, it might be for a safety application, um, it might be to prevent the spread of disease. A good example of that is of times where we don't or we can't identify negative effects when we develop something. Is the first one I like is DDT. It is a pesticide that is still used today in certain countries to control mosquito populations. Mosquitoes are vectors for a variety of diseases, and if you kill the mosquitoes, as the theory goes, they can't spread the disease. So DDT was sprayed all over the place, and within the span of a couple years, um, people started to realize that raptors' eggshells were not as thick anymore, and there's some mechanism by which the DDT interferes with the egg creation process in the female birds. So when they lay the eggs and they sit on, they get crushed. And so a lot of raptors went extinct. I can remember being a kid and we never really saw owls and eagles and hawks and stuff like that. Now they're all over the place because we realized something was going wrong. We had to correct it. Asbestos is another example. Um, Asbestos is banned now in a variety of countries, and if you're in the United States at least, and you go into older factories and industrial settings, you'll see all over the place. Don't disturb this wall. There's asbestos in here, or this pipe insulation has been asbestos remediated because it gets in your lungs and it can cause scarring tissue, and then you can't breathe. Another example, and asbestos is a mineral, that we've harvested for 4,000 years, and we didn't realize it was dangerous until we really started industrially producing it in the early 1900s. Lead pigments in paints are another one. In the United States, lead pigments in paint were banned in the 1970s. So if you have an older house, mine is from the 1930s, whenever we want to do some repairs or some changes to the house, we have to worry about fragments of lead dust. Makeup had lead paint in it, so you women use makeup, and I got people use makeup to paint their faces up and look nice when they're going places. And then the lead pigments were causing them to have all sorts of skin conditions. So then you had to use more makeup to cover up all the blemishes and things that the lead was causing until we figured out, hey, it's the lead, and we've developed alternative pigments. So we have to be careful when we develop a new piece of technology. What ill could come of this? Are we being careful about the environmental impacts, biological impacts, and the human impacts, and for just the environment at large, to make sure that we are doing our best to ensure that we're not causing harms by solving a problem? In chemical engineering, we always have this joke that we are paid to fix problems by developing chemicals for them, and then we're paid again to come back and clean up the problems that those chemicals caused. So if you think about those problems when you're designing something, that can help you to create stuff that have less of those problems and be a better environmental steward. Um, this is one of my favorite papers. I spent some time working on chemical warfare agent mitigation technology several years ago. Um, some scientists used drug discovery software and basically asked it to generate molecules that could bind acetylcholinesterase, which is an enzyme in your nerve cells, and it basically is what allows your body to move. And and I'm going to read these quotes directly because I think they're more impactful when you hear them, at least for me. Um, so they were wondering, can we make new chemical weapons with this software? Is that something that bad actors could use it for? And in less than 6 hours after starting our in-house server, our model generated 40,000 molecules that scored within our desired threshold. We did not assess the virtual molecules for synthesizability or explore how to make them with retrosynthesis software. For both of these processes, commercial and open source software is readily available that can be easily plugged into the de novo design process of new molecules. Basically, what that means in layman's terms is if you have access to one of these drug discovery softwares, you can ask it to make a molecule that is bad instead of one that's good. And retrosynthesis software, I'm going to give an example of that, I believe, on the next slide. Retrosynthesis software basically allows you to tell a computer, I would like to make this molecule. What precursors do I need to buy? What are the steps that I need to take? And under what conditions? So dangerous. This plot is a VX, which is a really well-known nerve agent. LD50 is the lethal dose 50. It is the concentration of a chemical that is enough to kill 50% of a test population. So you can see the further to the left you go on this graph, the lower a dosage of milligrams per a kilogram of some animal is necessary for it to die. And you can see the counts going up. They discovered stuff that is exceptionally lethal. So, how do you make sure that you keep the technologies you develop on a path for doing good. And thinking about that in the engineering process, even as like if you're doing a physics calculation, you check your units at the end. Even taking a little step to say, if somebody bad had this, what might they try to do with it, and how can I engineer it so that it's more difficult for them, can be really important in an engineering design process. And we often don't think about it because we're thinking about the good applications that we have for our technology. So AI in today's materials lab. These are things that have been published in the past couple years that I find exceptionally fascinating. This one on the left is retrosynthesis prediction, which, as I mentioned on the last slide, it's telling a computer, I would like to make this molecule. How do I do it? And it also works for materials. I'd like to make this alloy. What precursors should I use? How should I process them? Under what conditions? And these tools are really fascinating. Here, this algorithm is proposing a Grignard reagent, which is a magnesium chloride salt, as a way to react these two carbons together. So I think I can do this here if I use a little laser pointer. So you want to connect these two carbons here. And so what you do is you would have a magnesium chloride salt. The chloride dissolves, reacts in this location on this carbon. And then the magnesium uh, attacks in this position on this carbon here. And as the chlorine is removed, now you have extra electrons on this carbon and it forms this bond. The Grignard was, I believe, a French chemist who won a Nobel Prize for this discovery. But it's basically saying, yeah, this is how you complete this step. And it's not limited to one step. These things can make incredibly complex molecules and materials, and they're really, really powerful. On the right, we have inorganic crystal discovery. This is from a paper published by DeepMind, which is owned by Google and done in conjunction with Cal Berkeley. Um, they generated like 40,000 new crystal structures and then synthesized about 700 of them and checked for the predictions of stability that their AI agent had assigned to the new molecules. And they found exceptional agreement. So they have the ability to just brute force say, I'm going to discover a whole bunch of new molecules. I don't have an application. I don't know what I want to do with them, but can I predict the properties of them? Because the next logical step to that is I would like a molecule or I would like a crystal that has property X, make one for me or suggest one that I can make and tell me how to make it using retrosynthesis. Gas separation membranes. I had the opportunity to work on membrane technology about 10 years ago. Membranes have historically had reliability issues. They'll burst because of pressure gradients and things like that. But they have a lot of those technological problems have been solved in the past few years. And membranes are fantastic for gas separation purposes because there are differences in permeabilities between different materials. So a lot of gases require, if you were going to say do cryogenic distillation, you have to cool them down. It's exceptionally energy intensive to separate them. A membrane, you just flow gas through the fibers. If you're, for example, using hollow fiber membrane, and oxygen and nitrogen will diffuse through those fibers differently. So if you put a train of membranes together, one after the other, you can effect really nice separations with these. When you use AI, and these researchers, this paper is actually a review of a couple of different membrane technologies that are developed with AI. And one of the ones that they use is explainable AI. Normally, AIs are black boxes. So you say, make me this, and it will say, this is your answer. And you have no idea how the AI really attained that answer. This explainable AI that they're using is using shapely values. So that comes from game theory, which basically assigns credit for being correctness to different features of a model, which in this case are assigned to different features of the chemistry of these membranes. And that's not just applicable to membranes, that's applicable to any type of material science problem. It's saying what feature about this gives this material its mechanical stability, or what feature about this controls its ductile brittle transition temperature. And they also use this model to interpret the gas permeability predictions by a random forest and deep neural network program. So, really fascinating technology. This figure shows an application of Bayesian optimization to nanoporous materials generally. Um, and so, I'm going to talk about greedy functions for a moment. Basically, a greedy function is a function that identifies an unknown data point, which, if information was available about that data point, would maximally decrease the uncertainty of the function. And so that would be for this two-dimensional plot here. That would be right here. If you have a point right here, You reduce the uncertainty there, that will maximally decrease the uncertainty of this plot. So these are exceptionally powerful, and they're used for autonomous experimentation, which I'm going to talk about toward the end of this talk. And they're really fascinating to read about. I'd encourage anyone that's interested to take any of these references and read about in detail these technologies that might interest you. When you're doing something like this, that is the using a greedy function-based algorithm is one of the fastest ways to optimize a system. They're really powerful and really cool. Additive manufacturing metal alloys has become very popular recently because it allows you to make geometries that are not possible with conventional methods. It can also be a lot cheaper. I talked about tools that make tools that make tools. And if you have a laser powder bed fusion machine, you don't need to create all the tools to make a part. You can make a variety of parts without having molds, without having dies, without having presses, etc. Um, with any manufacturing method, there are difficulties with the technology. These plots are from laser powder bed fusion, and one of the a serious problem with laser powder bed fusion is called keyholing, which is where the metal boils if the laser power is a little bit too high, and it will not the so that boiling will create some gas, and you will not have or the bubble of gas will not have time to reach the surface before it solidifies. So you get these little keyholes in the material. These researchers created an imaging system for their laser powder bed fusion machine that tracked the laser, and they were able to train it by putting the laser into specific power and print speed regimes. So basically, how far linearly does it move in a second, and create some training data, and then predict for other metals what kinds of defects are going to be observed based on what the melt pool from the laser looked like, which is just utterly fascinating to me. So you're able to take a picture of what a melt pool looks like and say, you have keyholing in this part. Additive manufacturing of small parts presents less difficulty than large parts. When you start going to large parts, first of all, the metal powders are extremely expensive, so you'd like to waste as little as possible. But additive manufacturing is much slower per part than a conventional process. You can stamp out tons of car doors over a week's long span. You could probably only print one or two with most of the machines that are available today in a week. So you would like to use your machine optimally. You hopefully would not want to build a part as big as a car door and then only to realize after you have finished printing it that there's a defect in the first 3% of the build, and you have to scrap it and start all over again. So technologies like this are enabling in situ monitoring of additive manufacturing processes where you can stop your build at maybe 5% in because there's been a defect, and you can scrap it, identify from an engineering analysis what's causing that, change your parameters on your instrument, and save a whole bunch of time and money. Okay. So those are all things that have been published in the very recent past. What's in the future? The future we can see. One of the clear ways things are going is autonomous experimentation, and I've alluded to this a little bit a moment ago. Basically, how autonomous experimentation works is the entire materials discovery process is automated. So you might have some need to create an alloy that has a slightly better corrosion resistance than something you currently have available to you. Or maybe there is a raw material that's extremely environmentally hazardous to process, maybe a rare earth element that requires leaching and strip mining to procure, and you'd like to create something that doesn't have that problem. So you tell the computer, hey, I want to do this. I want to make some alloy. It has to have these material properties. It cannot have these elements. Figure out how to do it. And so it will run some computer simulations and predict some alloys, and then it will then communicate to an autonomous experimentation system, which might be over here on the left. We have this is a hood from ChemSpeed where they have some sample preparation tools, all automated. So it might start, it'll mix for you, it'll separate, heat, center, all those kinds of things. All those unit operations are available. And after the materials are made, a cobot will come or a robot will come and take those samples and put them over into your analytical equipment. The analytical equipment will maybe do XRD on the materials, X-ray diffraction, and feed that data back into your computer system, into your AI model. The AI model will process the diffraction patterns, identify some improvements to the material, and the process continues on this loop of optimizing your material until you get the desired product. I think this technology is going to revolutionize the way we do material science. If you are in graduate school now, you probably see all the extra things, I'll call them, that your advisor has to do. They're writing grants, they are advising you, they're maybe teaching undergraduates, they're reviewing tenure in the United States, they're advising junior faculty, they are peer reviewing articles for journals, they might be editors on journals. Um, they don't have time to really think. They don't have time to take a walk and think about an idea they have and how will I fix that problem? This kind of technology is going to change all of that. And I find the same thing in industrial settings too. People are so busy doing all of their responsibilities that they don't have time to take a walk and think, or take a shower and think about a problem that they're having they'd like to solve. Another example is personalized cancer treatments. We found out last year that my dad has a rare form of blood cancer, and his treatment involves, and so cancer treatments involve generally, but this one specifically is going to be DNA based. He's going to the hospital next week and they're going to extract some of his stem cells and do some medical stuff that I don't fully understand. But basically, how it works is they're going to take out some of his DNA, put them into these new stem cells, and try to grow some cancer free stem cells that they're then going to stick in his body. They're DNA tailored to him. And that is done through a lot of really interesting technologies. Um, but cancer generally, there are papers you can read about using image analysis to recognize whether a mole is melanoma or not, whether it's cancerous. Um, and a lot of pharmaceutical products are being developed that will take your genome into account in terms of what medication the doctor prescribes to you. So the AI inputs some data about what your skin might look like. Maybe you have a mole that you're worried is melanoma or another type of skin cancer, or maybe you have some other medical condition, and your DNA will be fed into an algorithm, and it tells the doctor, "Hey, you should prescribe this medication." And so the doctor does, and you have improved treatment outcomes. I remember when I was a kid, some of my friend, like people's moms or dads would get cancer and they'd lose all their hair through chemotherapy treatments. And I really rarely see that anymore. Our medical technology, I think, is one of the fastest growing fields of materials. And the things that we're doing with AI in terms of being able to identify conditions, to provide treatment recommendations, to summarize patient histories, all those types of things are really to improving patient outcomes. So, to start to wrap things up, when we make discoveries, we have specific mindsets about things. The technologies that I've talked about today have some really hardworking engineers and scientists developing them, and they had visions. They had things that they wanted to accomplish. They have objectives. Improving people's lives is a really great one that I really am personally connected to. It might be reducing an overdose or connecting people to more information. My wife is from India, and one of the things I found most fascinating is that as India has uh, increased its amount of people that have access to the internet, uh, she can do have study sessions and stuff like that with her cousins um, over the internet. And now we're starting to get a feedback loop where we had this joke in grad school that if you didn't understand something your professor said, you just go on YouTube and there was an Indian person there who could teach you exactly what was going on. So it feeds back into this information loop where everybody is able to benefit from access to the information. Modern cars now, they have crash detection. Someone will be distracted. Maybe their kid is screaming in the back seat because they dropped a toy. You reach back to get it, and the car goes, "Whoa, whoa, whoa! You're about to crash!" And it starts flashing, or your seat vibrates, or it even applies the brakes for you, so you don't get into a wreck. Environmental testing. I have a theory about a lot of organic chemicals as an example, where we develop things, we figure out that they're hazardous, and so then we find replacements. Bisphenol A is a recent one, polychlorinated biphenyls. Asbestos is one we talked about, where we use chemicals and materials for things, and then we discover that they're hazardous. And so we develop a new one, and we discover that that has some different hazards. So we develop a new one. And it's this continuous uh, race to find something that is minimally hazardous. And environmental testing is something that might help us to achieve those things faster. So, whatever field you're in, there's probably something that's caused you to be in that field. There's a reason you're in this session today. You're interested in a particular piece of technology and you want to do something with it during your life. The problems you solve are going to be hard. I talked a little bit about some of the difficulties that scientists and engineers have faced, like balancing their family life, the struggles to figure out how to do particular pieces of technology. If you read some of the histories of skunkworks, people yelling at each other, calling each other mean names, and things like that, because the stress and the tension can be really high when you're trying to accomplish these types of things. The thing that will help you persevere through those difficulties is the vision you have for what you want to accomplish and the things that give you inspiration. I highly recommend that you have those. If you don't have those, take a walk and think about them. Sit in a quiet room, go somewhere that has a nice view of nature, something that inspires you, and figure out what really motivates you to do engineering, to do science. And think about those regularly. So finally, we end up with you. And as I understand it, this is something you might be asked about later. So why are you here? Why are you in Womanium? What inspires you? What's your vision? And finally, what do you hope to accomplish in 5 years? This is, I think, one of my favorite interview questions. So imagine that you're interviewing for a company that you really want to work for your dream job. Figure out, what is that job? What do you want to do? You're nailing the interview. You have great answers. You have good chemistry with the hiring manager. You're laughing. You're making, having a good time. You're feeling really confident. And you're wrapping things up, and the hiring manager says, I have one more question for you. If I hire you, what will you have accomplished in 5 years? That's a really powerful question, because it enables a hiring manager to say, is this person, you can't, for example, you can't answer that question by saying, oh, like, I want to be a manager, or I want to be the general manager, or I want to be in charge of all this stuff. No, it's what piece of technology, what technical accomplishment are you going to have in 5 years? Because it lets the hiring manager see what your vision is, to understand your inspiration, so that they can understand how to best help you succeed and determine if you're a good fit for the role and if you really want that job. I have one of these written down. I always have my what do I hope to accomplish in 5 years for today. It's in the same file or the same folder where I keep my resume. And I highly encourage all of you, I think we still have a little bit of time. Hopefully, we will after questions. If you don't have an idea of what you want to accomplish for 5 years from today, take some time to write it, put it in a note on your phone, write it in a journal, put it in a file on your computer, but have some idea right next to your resume of what you want to do in the next 5 years. Because sometimes hiring managers won't ask you this question. At the end of their interview, though, they're going to say, do you have any questions for me? Or is there anything else that you wanted to know about our company, et cetera? And you could say, well, I just do have one thing that I want to share with you. If you hire me for this role, 5 years from now, I want to have accomplished X. Fill in that X with whatever it is that motivates and inspires you. And it will be a really great outcome for you from these interviews. That's my last slide. If anyone has put questions in the Discord, I assume that there might be a few. I'm happy to take those now.
Fantastic. Thank you, Jon, for this amazing and inspiring talk. And the first question is not from everyone to you, but from you to everyone. Namely, what do you hope to accomplish in 5 years? Can you share some answers on Discord, everyone? I'm sure you have dreams, you have goals, you have visions. And in the meantime, very positive feedback to your talk, Jon. And Nidia from the US shares, that is such a powerful message. Thank you, Jon. Hussein sharing, he wants to accomplish to write the first ever quantum computing killer app. This is a great point. The killer app for quantum computing has not been found yet. And wow, what would it be great if one of you could do that? Yara from Brazil and the US shares, she wants to build the quantum education community in Miami, Florida. Rajesh, write a good quantum computing algorithm that solves a practical problem and educate others on quantum computing. Nidia from the US, research on better medical advancements for mental health and autoimmune conditions. That is really a wonderful goal and vision. Joseph from the US, I want to build a camera that uses qubits as pixels. Oh, we can talk more about Joseph. Bavia, trying to find a solution to get rid of pollution. I want to build quantum communication systems for interstellar communication, is what Vikramaditya from India shares. Quantum wireless communications for 6G. Please, everyone, keep writing. This is great. And soon we will announce a happy hour for Sunday, so then we can talk more about it. I would like to continue in the meantime with questions to you, Jon. Izzy from the US asks, What do you think will be the new workhorse material, like steel, that revolutionized every industry? And then Izzy adds, will it be LK99, the superconductor that you alluded to?
That is a good question. It reminds me of Atlas Shrugged, which is a book by Ayn Rand, where one of her characters develop his last name is Reardon, and he develops what's called a Reardon metal, and it's cheaper and it's lighter, or not cheaper, but it's lighter and it's stronger, and they're using it to replace all their railroads. I think that we're about to witness an explosion in alloy development because of a variety of technologies, both the extraction of ores and the AI design, where you can ask an AI, I need to develop an alloy and it needs to be 5% lighter, or it needs to be lower assay than this alloy. I'm not sure what the exact alloy is, but I would be willing to bet that in the next 5 years there's some new alloy that is being used, whether it be for spacefaring applications, whether it be for quantum computing. I'm not sure, but I believe that it's coming, and it's coming quickly.
Can you also share a bit more about these refractory high entropy alloys that you mentioned in the beginning?
So a high entropy alloy um, has other names. A common one is a multi-principal component alloy. So historically, if you look at the history of metals development, the first metals were like, you'd get bronze, which is a combination of two metals. You have iron, and now we've really started to develop things where you might have three different elements in an alloy. Four high entropy alloys are unlimited, I guess, technically, in terms of the number of elements, up to the amount of elements that you can alloy into a metal. So you might have 5, you might have 10, maybe you have 15. Maybe there's no reason to have 15, but you will add trace amounts of an element into an alloy to give it a different property. So a good example is 316 stainless steel. There's low assay and there's high assay stainless steel. So 316L and 316 high, where you have or the carbon amount in it. So 316L has like 0.003% at most carbon, and 316H has 0.04% carbon. And those differences, 316L is better for welding applications, and 316H is harder. So when you add small trace amounts of elements into alloys, you can change their properties and make them more suitable for an application. Um, if if you imagine a situation where you needed to create an alloy, and you're doing it with an AI, and you give it the constraint, like, you can have at maximum 8 elements in this, and you can pick from these 30 elements, you're getting into combinatorics, and there are millions of possible combinations. It's impossible to run density functional theory on that many combinations. It's certainly impossible to do high throughput experimentation on those number of combinations. So that's why I think AI is really going to change the high entropy alloy space. And then the first word of that is refractory. So refractory alloys are for really high temperature applications. Um, there's a company in Austria called Ponzi that is a world expert in these, and they're starting to push a lot of new technologies in this space, where you'll have an alloy that can withstand really high temperatures. And I guess one of the first examples that comes to mind for me is hypersonic uh, missiles is something that a lot of militaries are developing. You need alloys that can withstand those temperature gradients. Um, Fusion reactors, you read about some of these experiments where temporarily the experimental setup is the same temperature as the sun, and it's temporary because of the energy requirements, but also because of the material's abilities to withstand those temperatures. So that is, I guess, kind of my perspective on what refractory high entropy alloys are and how they'll be used. And I think a lot of it is dependent upon using AI to discover them, just because the possibilities are too numerous for a reasonable theoretical or experimental conventional effort.
Wonderful. And you really took us into history. Really inspiring and insightful talk. Mohammad Reza from Iran asks, how to make sure AI won't manipulate the successions of material discovery developments to ensure safety for human purposes? And then he adds, would assume evolution for selection applies here.
AI is going to give us the same technological problems that every other piece of technology has given us. We don't know how to do things that we used to be really good at doing. Um, like that medical records example I gave, like the nurse was having trouble writing the medical record. The same applies from a technological standpoint. When I was in engineering school, I learned how to do drafting with a pencil and engineering paper. And most universities in the United States don't even teach that anymore. They maybe will spend 1 week covering, hey, this is how you draw out a part on a piece of paper because everything is CAD now. So if the computers go away, like if we had a strong solar pulse and it disabled a lot of our electronic systems and computer systems, we wouldn't have the institutional knowledge to draw parts, to draw things that we might need to um, repair pieces of technology, and that could be a serious threat to humanity. Um, we had those strong solar storms about a month ago where people were worried that the electronics would get fried, as an example. AI is going to give us those same types of problems. And it is our job as engineers and scientists to decide to what extent we are going to allow AI to do things for us. And to what places where we say the risk of humans not knowing how to do this anymore is too great. An example I heard recently was reading and summarizing articles. And the speaker said, "Oh, like this is fantastic. I can't wait for this because it's really tedious to read an article and then summarize it. And if you have to read a whole bunch of articles and summarize them, then you start getting fatigued. You're reading for hours, and your quality of writing, your summaries goes down with time. The problem is if you ask an AI, hey, summarize this 30 or 40-page document, or maybe summarize a small book for me, you don't have access to any of the information other than what the AI tells you. And if the AI doesn't specifically know what you know, it won't be able to tell you, hey, there's this particular passage that 95% of people won't care about. But because of this unique background you have, or maybe you had some internship with a company, you'll be interested in this particular aspect of the technology. And so I'm telling you about it. If the AI doesn't have the ability to know who you are, what you know, um, and tailor a response specifically to your information, then you're putting yourself at a huge risk of information loss in institutions. So, safeguarding ourselves, I think the easiest way to do it is say, do I really need AI to do this? Should I adopt it in a limited sense? And what countermeasures should I take to ensure that I still have the ability to do particular aspects of this work myself if I need to? Are really important. And the problem is the risks for some of these things like solar storms are so low that we say, yeah, we're not really going to worry about that much. But if one of them comes, maybe it's once in 1,000 years and wipes out all of our technology, it could prove to be extremely hazardous to the human race. Your comment about evolution, I think it's everything evolves, species evolve, societies evolve, and I think it's probably correct that AIs will evolve too. From a technical standpoint, if we created an artificial general intelligence, the fear is that it will figure out, hey, I can order myself some new power supplies and I can get more energy, and I can order myself some more hard drive racks and a couple SSDs and some GPUs, and I can, pay somebody on TaskRabbit or Fiverr or one of these other apps to come over and install it while the scientist is away because I know his schedule. And the next thing you know, guy comes in and the AI has taken over a couple of robots. It's like the sci-fi horror story, right? So we have to continuously think about the technology we're developing and say, how can we make sure that this doesn't go wrong? Or at least do our best effort to make sure that it doesn't go wrong.
Fantastic. And I see a lot of people agreeing with you. And thank you for that.
That's good.
Great.
um,
Shoot.
I'll give a short story. I was at a conference about 2 months ago, and there was a senior scientist giving a presentation about AI for materials discovery from a more technical standpoint than my talk. And so I brought up this Nature paper about discovering chemical warfare agents to him, and I said, "Look, like, what do we do to fix this?" And he kind of avoided the question, like, how do we design technologies? He said, "Oh, well, you just have to be careful." But he was kind of avoiding the point because I think he was so caught up in the positive benefits of being able to use AI for materials discovery that he's not willing to look at the risks. So I'm glad to hear that the younger crowd is realizing, hey, like things can go wrong if we're not careful, because it really comes down to each of your specific engineering and scientific challenges. What's going to happen with this in the wrong hands, or what's going to happen with this if it has some type of problem, and how do I fix that? How do I avoid that?
Maya asks, Are there any constraints on what kind of materials can be found by AI? For example, can we generate petrol-like materials? Then Marcia asks, what is the percentage of chemicals found by AI that are actually viable, that can actually be synthesized? And then Osama from Egypt asks, how massive does the data need to be for AI to be more accurate in building models? I'm sure you have to say something about that. Constraints,
Yeah, so
kind of
I'm going to
materials.
start with the last one first. I think the analogy that's easiest to understand is if all of the possible materials just based on combinations of elements was represented by the size of the known universe, the volume that we have discovered is a cubic nanometer. There are so many possible materials that exist that it's very hard to train more of, I guess, what I'll call like a more conventional or traditional AI, where you train it on some data and then ask it to make new predictions, because it can be limited to the parameter space of that data. I think generative algorithms and physics informed, so they're called physics informed GANs, and so you can apply a physics based constraint. So maybe you could apply a stability condition, like that the Gibbs free energy of this material has to require or has to mandate that it is actually a stable material, as an example, and say, okay, so generate these and then do this energy calculation on the materials so that you only propose ones to me that are stable under some given conditions. So I think that answers part of the second condition, or the second one of those other three questions. And the third, I think, if I recall correctly, was what percentage of material or of chemicals have been discovered with AI. And there was also, um, can I think it was can AI discover like petrochemical based chemicals? And I think both of those questions are good and can kind of be answered. So I talked about the retrosynthetic analysis. And I also mentioned that I am an applications person. I'm thinking I want to make a product. What do I need to make that product? And when you approach a problem from that direction, you can use something like a retrosynthesis algorithm, and they're very, very good. Marlou, I can give you all the references for these if you want to spread them around, but that paper where they talk about the retrosynthesis, or you can just look at retrosynthesis of organic compounds, do like a Sci-Hub search or a Sci-Finder search for those. And you'll see the power of these and saying, I need to make molecule X, and it will give you really reliable reaction pathways. And sometimes you can actually go back and update those reaction pathways and say, hey, I tried this and it didn't work. It failed at this step. Propose me a different process, but use all the previous steps you'd suggested up to step 5. Give me something different. So I think it's there. I think it's possible. And when we talk about plastics, especially the environmental hazards of plastic waste, and I've traveled a little bit around the world, and I remember I was in India, and we stopped at a coconut stand, and the guy chopped the top of the coconut off with a machete and give you a plastic straw, and his disposal method was throwing the coconuts and the straws on a pile behind him. And so a lot of those stuff, that's just one example I've seen. It happens all over the place. We put in America, we put plastic in the recycling bins, and then we find out that it ends up in landfills, or when it's processed, a bunch of it ends up as microplastics in wastewater streams that pollute our waterways. So engineering plastics to make them biodegradable, I think, is going to revolutionize the plastic recycling problem. Because if you can just throw a plastic into a regular landfill stream, you're not worrying, and it's biodegradable. And for reference, if you've seen some of the, like, I see silverware a lot, cutlery, that says it's biodegradable, but it'll say, oh, this needs an industrial composting facility. You can't put this in your backyard compost pile and expect it to degrade. Engineering new plastics that will biodegrade and being able to control how long their life should be so that it lasts for the desired need of that product, but afterwards it will degrade quickly, could really revolutionize a lot of the microplastics and the ocean plastic pollution problems that we have.
Great. Jon, thank you for this answer, and thank you for this wonderful and inspiring talk. We could organize a separate Q&A session with you just to talk about many things. It will be amazing and very exciting. For now, we will move on to the second talk of today. Jon Ruffley, thank you very much for this inspiring talk, and we will be in touch.
Great. Thanks very much for the opportunity. and I'm always happy to talk more about this stuff. Thanks a lot, everyone.
I will flash 3 slides before we enter Sam Stanwyck's talk from NVIDIA on AI, HPCs, and quantum. Yes, here we go. The screen share is on. This Sunday, same time as the live sessions, we will have a happy hour for an hour. Join to meet each other, share your story, talk about quantum, talk about life, get to know each other globally. We really look forward to a more personal hour all together. So hope to see you there. Same Zoom link, we will send a reminder. Then second, the certificates are within reach, the first certificates at least. On Sunday, June 23rd, so this Sunday, the Q Bronze quizzes will be due, 50% per quiz, 70% overall. And if you achieve that, you will earn the Q World Q Bronze certificate. If you are joining just now and it is impossible to make that, don't worry, just do the module and it will count towards your final certificate of achievement. And I will share more about this at the end of the session. And now just a quick overview. 1 week later, Sunday, June 30th, you can finish assignment 6.6 to earn the classic quantum algorithms design first certificate. I will also share more details on that at the end of today's session. Third, a couple of shout outs. You have really been supportive to each other, collaborating so well. And I will highlight more and more people who are contributing so much. And today's highlight is for Hussein Shiri from Lebanon, who has been helping everyone continuously and so elaborately. Please and applause for Hussein Shiri. And then a few media shout outs. There have been elaborate posts on LinkedIn about the program. For example, here from Mohammed Alamin Ali about Wednesday's session with OQC. Then Sujit has even started writing Medium articles about the session. For example, here about Monday's talk on AI for climate with Kalai Ramia, and also posted about that on LinkedIn. If you post on LinkedIn, please tag @Womanium, because then we also see it and can share it further and share it among each other here too. That was very brief, and at the end of the session, we will discuss that more. But I don't want to take more time from our second speaker, Sam Stanwyck.